All right, so today we're going to talk about limits involving infinity. Okay, in 2.1 we talked about limits according just with limit approaching x approaches c or anything like that. Today we're going to talk about limits approaching involving infinity. So let's see if we can figure this out. So if I had y is equal to 1 over x, it's going to go like this, right? So the limit as x approaches infinity, positive infinity is what? As x approaches infinity, goes out this way all the way to the end, 1 over x is going to be equal to 0. It's going to be trying to get to 0, but it never quite gets there. As x approaches negative infinity, which would be that way, right? If I go that way, it's still 0, right? Because this guy tries to approach 0, but it never gets there, right? Okay. And we already know that these are called horizontal asymptotes because it's an asymptote because it tries to get there but never gets there, right? It's an asymptote. So you go to page 70 in the middle, there's a green box with the definition there of the horizontal asymptote. The line y equal b is a horizontal asymptote of the graph if either this is b or this is b, okay? All right. So do the horizontal asymptotes are they always the same? Well, the answer is no. If you look to example number 1, where you have f of x is equal to x over root x squared plus 1. And if you graph this, and that's one of the things, another thing about limits is that you should always graph it just to make sure that you are correct, right? The graph goes like this, actually. It's like this. Okay, so when x goes to the limit of x, when it goes to positive infinity, is 1, because it tries to get to 1, never gets there. Limit as x approaches negative infinity this way, so it tries to get to -1, but it never gets there. Okay, so as you can see, you have two different horizontal asymptotes. So you have an horizontal asymptote, but it's different. So when it goes to the right end positive infinity, it is 1. When it goes to the left end, negative infinity, is -1. Okay, all right. That's that. And then we have on page 71 a squeeze theorem revisited. And on this one, we're going to do the sine x over x one more time. So example number 2, we're talking about f of x is equal to sine x over x. Remember, the graph looked like this. So to go out like that. Okay, now, so earlier when we said we talked about this, and we said that the limit when x approaches 0 was 1, because it tries to get 1 to 1, but it never gets there. Now, in this one, we're going to talk about the right end behavior, or the when it goes to x goes to infinity, right? We have sine x over x. This is what we're trying to find. Okay, and you can tell that it's going to go like this, and it's going to go get to 0. Does anybody remember what we called this? There was a specific name for this in honors pre-calc. It was called damped oscillation. Damped oscillation. Does anybody remember that? Remember we had some things that went like this, and we went up and down and in between. We had the graph that went like that, and we called it dampened oscillation. Okay, so this is what we're talking about here. Okay, so now we want to talk about how it goes over here. So graphically, we can see that it's going to go to 0. Now let's see if we can go ahead and prove this. Okay, so the way to prove this is to say that sine of x is going to go to between and -1, right? Because by definition, sine x is bounded upper and lower by -1 and 1. Now I'm going to divide by x. Now when I divide by x, and this is a tricky thing, right? Because when I divide by x, I have to, when I multiply or divide by anything, what do I have to look at? I have to consider whether it's negative or positive, right? Okay, now in this instance, I'm not going to have to change these because x is going to positive infinity. Okay, I'm taking x to positive infinity to the right-hand behavior, so I know that it's a positive number, so I don't have to change this. Okay, now I'm going to go ahead and take the limit x goes to infinity on all of these, okay? Limit x goes to infinity, limit x goes to infinity, x. So I know this guy, as x goes to infinity, if I put a billion here, I get -1 over a billion, which is basically 0, right? Over here is the same thing, right? 1 over a billion is 0. So that tells me that x goes to infinity, sine x over x, and this guy here has to go to 0 because it's squeezed between these two zeros. Okay, all right. Bottom of page 71, there's a green box. Properties of limits as x goes to positive or negative infinity. Go ahead and review that. It's basically the same thing as you had in 2.1, but instead of c, you're going to have the positive and negative infinities there. So go ahead and read that, see if it makes sense to you. Okay, if there are no questions on that green box, let's move on to example number 3. Example number 3, we have this guy. And this is basically what? This becomes limit as x approaches infinity. I'm going to do this guy here, and that's going to be 5. And then I'm going to do this guy here. I'm going to have plus sine x over x. Okay. And the previous one, I just found out that this guy here is going to go to 0 as x approaches infinity. So what do I have left? All I have left is 5. Okay. All right, let's go to the bottom of page 72. It says infinite limits as x approaches A. So now here we're going to talk about the vertical asymptotes. So far we've talked about the horizontal asymptotes. Now we're going to talk about the vertical asymptotes. Okay. So if you go to the bottom of page 72, it says the vertical asymptotes. There's a definition there. The line x equal a is a vertical asymptote of the graph of y is equal to f of x if either as x approaches a from the positive side, it becomes positive or negative infinity, or from the negative side. So either as x approaches a from the positive side, f of x becomes plus or minus negative infinity, or if x approaches a from the negative side, f of x is plus or minus infinity. Okay, and this is a vertical asymptote. So this is a mathematical definition of a vertical asymptote. You already know what a vertical asymptote is. You've seen these before. Basically, when does a function have a vertical asymptote? Anybody tell me? Let's go ahead and graph this and find the vertical asymptotes for me. Graph this and find the vertical asymptotes for me. What do you get?
One and negative one.
1 and negative 1, right? And the reason being is because x squared minus 1 is x plus 1, x minus 1, correct? In other words, you're going to have a vertical asymptote whenever the denominator goes to 0, right? Because the denominator can never be 0, right? So when the denominator tries to go to 0 is when you're going to have a vertical asymptote, okay? Right? Unless you're dealing with a trig function, right? So if I have y is equal to tan x pi over 2, 3 pi over 2, right? So y equals tan x. So the limit as x approaches pi over 2 from the positive side of tan x is what? I approach y is equal to pi over 2 from the positive side. It's going to go down this way. So this is going to be equal to negative infinity, right? Limit as x approaches pi over 2 from the negative side. If I approach pi over 2 from the negative side, it's trying to go up this way, right? So the limit is going to be positive infinity. Okay? And well, there is no numerator, denominator here. Well, there is. You just don't see it, right? Because this is the same as sine x over cosine x, right? And cosine x goes to 0 at pi over 2. And that's why you're seeing the vertical asymptotes there, okay? All right, so that's an example number 5. Example number 4, find the vertical asymptotes of that. Okay, so y is equal to, so this here was example number 5, okay? I did example number 5 early. Now let's go ahead and do example number 4. And example number 4, you're going to have y is equal to 1 over x squared, right? So where do you think you're going to have a vertical asymptote? When this is 0, right? When does this become 0? And x equals 0. So actually, if you graph it, you're going to graph out something that looks like this. Okay? So whether you approach 0 from the positive side or from the negative side, the limit as you approach x from the positive side, or if you approach x from the negative side, 1 over x squared is going to be equal to infinity. 1 over x squared. Both of them are going to be positive infinity. Okay, so there you go. So that's why this is a vertical asymptote. Okay? Any questions about what we discussed so far? Are there any questions? Okay. If not, I'm going to go ahead and let you guys start working on the homework.